Molecules are chemically bonded groups of atoms that have a three-dimensional structure. Each molecule has a specific shape that is due to the types of atoms involved and the arrangement of electrons within the molecule. The way a molecule is arranged is referred to as its molecular structure. Understanding the forces that hold a molecule together allows predictions to be made about the shape of a given molecule. In this program, you'll see how molecular shape is determined. You'll also see how molecular shape affects interactions between molecules. The way these interactions can affect such things as the melting and boiling points of a substance will also be addressed. It is necessary to have a basic understanding of electron orbitals to understand how to determine molecular shape. Within an atom, electrons exist at various energy levels, each successive level being higher in energy and, in general, farther from the nucleus. Within the energy levels, there are various orbitals in which the electrons can be found. While there are various types of electron orbitals with designations like S, P, D, and F, for the purposes of this lesson, only the S and P orbitals will be discussed. Both the S and P orbital types have characteristic shapes. The S orbitals are spherical, with the nucleus of the atom in the center. There is only one S orbital per energy level. The P orbitals have a two-lobed structure, with the lobes on either side of the nucleus. As many as 3 P orbitals can exist at the same energy level. When they do, they are perpendicular to each other in space. The overlap of electron orbitals leads to the formation of chemical bonds. The lowest energy state of an atom is called the ground state. In this state, the electrons can be assigned to particular orbitals in a systematic fashion. This is done with an orbital diagram. An orbital diagram arranges the energy shells in order of increasing energy. An energy shell consists of all the orbitals at that energy level. For example, the second shell consists of the 2s and 2p orbitals. The lowest energy orbital, the 1s orbital, is placed at the bottom of the diagram. Arrows representing electrons are placed in the orbitals one at a time. No orbital can have more than 2 electrons in it. When all of the orbitals at an energy level are filled, electrons are placed at the next higher level. When there is more than one orbital at the same level, put 1 electron in each orbital before placing 2 in any of the orbitals. An orbital with only 1 electron in it is called a half-filled orbital, and as you will learn, these orbitals are very important for bonding. For an example of how to assign electrons to orbitals, consider the oxygen atom. The atomic number of oxygen is 8, which means there are 8 protons in the nucleus. Atoms are electrically neutral, so there must also be 8 electrons. An orbital diagram shows the distribution of these electrons among the orbitals. The first electron goes into the 1s orbital. Since there are no other orbitals at that energy level, the second electron must also go into that orbital. Now this orbital is full, and we move up to the next energy level. The third electron and fourth electron both go into the 2s orbital, because there are no other orbitals at this energy level. Now we move up to the 2p energy level. The first electron goes into the first orbital. Because all similar orbitals within an energy level are each half filled before any are filled, the second electron goes into the next open orbital, and the third goes into the last empty orbital. We have 1 electron left to distribute. It goes into one of the half-filled 2p orbitals. An oxygen atom can be seen to have 2 filled s orbitals, a filled p orbital, and 2 half-filled p orbitals. When an atom bonds to other atoms, it is generally only the outermost shell of electrons that forms the bonds. The electrons capable of forming bonds are called valence electrons, and the orbitals that they occupy make up the valence shell. For convenience, usually only the outermost valence shell is diagrammed when discussing bonding. For example, in oxygen, only the 2s and 2p orbitals would be depicted as the valence shell, because the 2s and 2p orbitals form the outermost shell. When the orbitals of valence electrons from two atoms overlap, a bond forms between the atoms. This kind of bond is known as a covalent bond. In the covalent bond, the electrons of two atoms are shared between the atoms. When a covalent bond is formed, the electrons no longer occupy the electron orbitals from which they came. They are now in a new molecular orbital with a different shape and size. Knowing that a covalent bond contains two shared electrons, we can draw diagrams that account for valence electrons in a molecule. These diagrams, named Lewis structures in honor of their inventor Gilbert Lewis, provide a means of determining valence electron distribution in molecules. Knowledge of electron distribution will be essential for determining molecular shape later in this program. It is assumed you already have some familiarity with Lewis structures, so only a brief review is provided. For a more detailed treatment of Lewis structures, refer to the CyberEd program Ionic and Covalent Bonding, or consult your textbook. Lewis structures provide a basis for the more detailed treatments of molecular structure introduced in this program. To show the Lewis diagram for an atom, write the chemical symbol for the element, for example, C for carbon. Then surround the atom with dots, one for each of the valence electrons. In this case, these would be the 2s and 2p electrons. Carbon has 2 electrons in the 2s orbital and 2 electrons in the 2p orbitals. Place 1 dot on each side of the atom before placing 2 dots on any one side. Here are the Lewis diagrams for 2 more atoms: nitrogen, which has 5 valence electrons, and oxygen, which has 6. When making Lewis structures to illustrate bonding in a molecule, it is important to note that most atoms tend to form bonds that lead to 8 electrons in their valence shell. This is known as the Octet Rule. When an atom shares electrons with another atom to form a covalent bond, count the bonding pair as 2 electrons for each of the atoms. For example, in the bond between 2 fluorine atoms, the pair of electrons involved in the bond would be counted as 2 electrons when counting electrons around the left fluorine atom, and as 2 electrons when counting electrons around the right atom. A variation of the octet rule occurs when hydrogen forms bonds. Hydrogen has only 1 electron, which is in the 1s shell. It forms bonds that lead to filling that shell, which only requires 1 more electron. To see an application of the octet rule, consider the diatomic chlorine molecule, which is 2 chlorine atoms covalently bonded together. The Lewis dot diagrams for the 2 chlorine atoms have 7 dots around each atom. That is, they have 7 valence electrons. The atoms combine by the 2 single electrons pairing and forming a bond. A bond is generally represented by a solid line. This sharing yields 8 electrons surrounding each chlorine atom. To see why this is, look at the chlorine atom on the left. It has 3 pairs of non-bonding electrons and 1 pair of bonding electrons surrounding it. Remember that the bonding pair, which is the shared electrons, counts as a pair of electrons for both atoms. This means that the chlorine atom is surrounded by 8 electrons. A non-bonding pair of electrons is also called a lone pair. Lone pairs are important in understanding the shapes of molecules, as will be shown later. Now examine the Lewis structure for carbon tetrachloride, a common laboratory solvent. In general, the first atom in a compound's name will be the central atom. The prefix tetra in tetrachloride comes from the Greek word for four. So, 4 chlorine atoms bond to the central carbon atom. Each chlorine atom has 7 valence electrons. The carbon atom has 4 valence electrons. The single electron from a half-filled orbital on each chlorine atom forms a bond with one of the carbon electrons. A check of each chlorine atom shows that each is surrounded by 8 electrons, 6 from the 3 lone pairs and 2 from the bonding pair. The carbon atom is also surrounded by 8 electrons, 2 from each of the 4 bonding pairs. Thus, each atom in carbon tetrachloride fulfills the Octet Rule. Sometimes more than one bond forms between 2 atoms in a molecule. These cases are treated in the same fashion as molecules with single bonds. For example, in the carbon dioxide molecule, carbon forms double bonds to 2 oxygen atoms. Looking at the Lewis structure, we see that the carbon atom has 8 electrons around it, 2 for each of the 4 bonds. The 2 oxygen atoms also have 8 electrons around them. Each has 4 electrons from the double bond from carbon and 4 from having 2 lone pairs. Triple bonds, which have 3 pairs of shared electrons, are treated in a similar fashion. Lewis structures are useful for showing which bonds are formed in molecules, and for showing the presence of unpaired electrons. But do they give a picture of molecular shape? To answer this question, take a look at the ammonia molecule. Ammonia consists of 3 atoms of hydrogen attached to a central nitrogen atom. From the Lewis structure, you might think that ammonia is a T-shaped molecule. However, experimental evidence shows that ammonia molecules are actually shaped like pyramids. In the next few scenes, you'll learn ways of predicting molecular shapes based on Lewis structures. Most common small molecules have one of 5 shapes: linear, trigonal planar, tetrahedral, pyramidal, or bent. In a linear molecule, all of the atoms lie in a straight line, as occurs in beryllium chloride. Trigonal planar molecules have 3 atoms at the corners of a triangle, with the central atom lying in the same plane. Boron trichloride is a trigonal planar molecule. Tetrahedral molecules, like methane, are 4-sided structures with an atom at each corner and the central atom inside. A pyramidal molecule looks like a shortened pyramid with a triangular base and resembles an open camera tripod. Bent molecules, such as the water molecule, consist of 3 atoms that do not fall on the same line and are shaped like a boomerang. In the first 3 common molecular shapes, linear, trigonal planar, and tetrahedral, there is a characteristic angle formed between the central atom and the outer atoms. In linear molecules, this angle is 180 degrees, and the atoms fall on a straight line, like the pom-poms and the head of this cheerleader. Trigonal planar molecules have an angle of 120 degrees, and the outer atoms form an equilateral triangle, like a propeller. Tetrahedral molecules have angles of 109.5 degrees, and the molecule looks like a jack. Notice that in these cases, the non-central atoms are arranged as far apart from each other as they can be. This is not the case in bent or pyramidal molecules, which have angles close to 109.5 degrees. As you will see, The reason that the atoms in the first three cases are as far apart as possible, and that the atoms in the last two cases are not, can be explained by a theory called the Vesper Theory. Vesper stands for Valence Shell Electron Pair Repulsion. Vesper theory states that electron pairs in the valence shell of an atom exert a repulsive force on all other electron pairs in the valence shell of the atom. This repulsion is due to the negative charges on the electrons. Remember that each bond in the atom represents an electron pair. Looking at beryllium chloride, you can see that the two bonds arrange themselves as far apart as possible, which is a 180-degree angle. In boron trichloride, the three electron pairs that form the bonds also maximize the distance between themselves, resulting in 120-degree angles. In methane, the same effect between the four electron pairs of the four carbon-hydrogen bonds leads to 109.5-degree angles between hydrogen atoms. Vesper theory has worked well to explain the shape of linear, trigonal planar, and tetrahedral molecules. It can also explain the pyramidal shape of ammonia and the bent shape of water. An examination of the Lewis structure of ammonia shows that not all of the electron pairs are involved in bonding. A pair of electrons in the valence shell of the central atom that is not involved in any of the bonds is referred to as a lone pair. Lone pairs of electrons exert repulsive forces in a fashion similar to electron pairs in bonds. In fact, because the lone pair is held closer to the nucleus of the central atom, it has a slightly larger repulsive force than do bonding pairs, and therefore pushes other pairs further away. How many electron pairs are there around the nitrogen atom of ammonia? There are 3 pairs of electrons in the nitrogen-hydrogen bonds, and another non-bonding pair for a total of 4 pairs, which satisfies the Octet Rule. The 4 electron pairs will orient themselves to be as far apart as possible. As in the example of the methane molecule, we would expect the bond angles between hydrogen atoms to be 109.5 degrees. Experimental data indicate that the actual angle is 107 degrees. This is very close to the prediction, and the higher repulsive force of the lone pair can account for the difference. Vesper theory also applies to a water molecule. Look at the Lewis structure. How many electron pairs are there in a water molecule? There is 1 pair of electrons bonding oxygen to each hydrogen atom, and there are 2 lone pairs giving a total of 4 electron pairs. As was the case with ammonia, the 4 pairs of electrons will arrange themselves in a tetrahedral fashion. Therefore, a prediction could be made that the bond angle between the hydrogen atoms would be 109.5 degrees, or slightly less due to the increased repulsion of the 2 lone pairs. Experiments show the bond angle in water is 104.5 degrees, so the prediction agrees with observations. It is important to note something about the shapes of the molecules in the 2 previous examples, which were water and ammonia. In both cases, the 4 pairs of electrons were arranged in a tetrahedron around the central atom. This did not lead to a tetrahedral molecular shape, however. The shape of ammonia is shorter in 1 dimension than a tetrahedron, and is referred to as pyramidal. The structure of a water molecule is like a boomerang with an angle of 104.5 degrees, and is called bent. When determining the shape of a molecule, just the position of the bonded atoms determines the shape of the molecule. Lone pairs of electrons are not part of the molecule's shape. To see how the position of bonds affects the shape of a molecule, try to predict the shape of a molecule not yet discussed, phosphorus trichloride. First, draw the Lewis structure. Phosphorus is the central atom, and it has 5 valence electrons, because there are 2 3s and 3 electrons in its outermost shell. The prefix tri means 3. Therefore, there are 3 chlorine atoms, each with 7 valence electrons. The 3 chlorine atoms share electrons to bond with 3 of the 5 valence electrons in phosphorus, leaving 1 pair of non-bonded electrons on the phosphorus atom. This is a lone pair. Adding the 2 electrons from the lone pair to the 2 electrons from each of the 3 bonds phosphorus forms with chlorine yields 8 electrons, which means the phosphorus atom satisfies the Octet Rule. This leads to a prediction that the pairs of electrons are arranged tetrahedrally around the phosphorus atom. However, lone pairs are not part of the molecule's shape, so the chlorine atoms bound at 3 of these 4 sites indicate a pyramidal structure for phosphorus trichloride. Experimental evidence has shown that the molecule is in fact pyramidal. Many molecules, such as formaldehyde and hydrogen cyanide, contain 2 bonds, or even 3 bonds between 2 atoms. 2 bonds between atoms is called a double bond, and 3 bonds between atoms is called a triple bond. Collectively, double bonds and triple bonds are called multiple bonds. How does Vesper theory handle multiple bonds? In Vesper theory, predictions of shape, each multiple bond is treated as if it were a single bond. To demonstrate what this means, take a look at the molecular structure of formaldehyde. The Lewis structure of formaldehyde shows that there are single bonds between each of the 2 hydrogen atoms and the carbon atom, and a double bond between the oxygen atom and the carbon atom. There are no lone pairs around the carbon atom because all of carbon's valence electrons are involved in bonds. Treat the double bond as if it was a single bond, and the oxygen atom and the hydrogen atoms orient themselves as far away from each other as possible, forming a trigonal planar molecule. The hydrogen cyanide molecule, which has a triple bond, can be analyzed in the same fashion. The central carbon atom forms a single bond with 1 hydrogen atom and forms a triple bond to the nitrogen atom. There are no lone pairs of electrons on the carbon atom. Again, treat the multiple bond as a single bond. The 2 bonds arrange themselves as far apart as possible from each other, resulting in a linear molecule with a bond angle of 180 degrees. You have seen that many molecules, such as methane, form 3-dimensional structures that are based on the shape of the tetrahedron. In the carbon atom of methane, the valence electrons that bond to the hydrogen atoms are found in the 2s and 2p orbitals. Recall that the shape of the 2s orbital is spherical. The 2p orbitals are 2-lobed structures that are perpendicular to each other and line up on the x, y, and z axes. Since this is the case, one might expect that there would be 2 distinct types of bonds, one between a hydrogen atom and the s orbital, and another between the p orbitals and 3 hydrogen atoms. It might also reasonably be expected that hydrogen atoms line up 90 degrees from one another in the bonds with the p orbitals. However, this is not the case. The bonds in methane are uniformly 109.5 degrees, and all of the bonds have the same character. How does this occur? The formation of new orbitals, called hybrid orbitals, explains how. Take a look at the valence shell of carbon. In the lowest energy state, called the ground state, the 2s orbital is full. 2 of the 2p orbitals are half-filled, and 1 of the 2p orbitals is empty. In this configuration, there are only 2 bonding electrons available, since the 2s shell is full. Because of this, you might expect that carbon would form bonds with only 2 hydrogen atoms. However, you have seen that there are 4 hydrogen atoms in the methane molecule. To allow the creation of 4 equivalent carbon-hydrogen bonds, a new set of orbitals is created in the atom. These new orbitals are termed hybrid orbitals. Hybrid is a term that is borrowed from biology and refers to something new being created from 2 dissimilar sources. For example, when a horse is crossed with a donkey, the hybrid offspring is a mule. Hybrid orbitals are a new kind of orbital created by the mixing of s and p orbitals and occupied by the electrons from those orbitals. The new orbitals have their own character separate from that of the original s orbital and p orbitals. When blue and yellow paints are mixed, a new color is created. This color, green, is neither blue nor yellow and is in fact something new. Similarly, when an s orbital and 3 p orbitals mix, new orbitals are created which are neither s orbitals nor p orbitals. These new orbitals are called hybrid orbitals. The shape of a hybrid orbital is different than either an s orbital or a p orbital. The s orbital is spherical, and the p orbital consists of 2 equally sized lobes on opposite sides of the nucleus. The hybrid orbital consists of 1 large lobe and 1 small lobe on opposite sides of the nucleus. For simplicity, the smaller lobe is generally not included in drawings of hybridized atoms. The larger lobe extends farther from the nucleus than either the s or the p orbitals. Because of this, the hybrid orbital can overlap more efficiently with orbitals in other atoms, leading to more stable bonds than those made solely with s or p orbitals. An s orbital can hybridize with 1, 2, or all 3 of the p orbitals. The number of new hybrid orbitals created is equal to the number of p orbitals involved, plus 1 for the s orbital. In other words, when an s orbital hybridizes with 1 p orbital, 2 orbitals, named sp orbitals, are created. When an s orbital and 2 p orbitals hybridize, 3 orbitals, called sp2 orbitals, are created. When an s orbital and all 3 p orbitals are hybridized, 4 orbitals, called sp3 orbitals, are created. The superscript indicates the number of orbitals of that type involved. Where there is no superscript, it is understood that only 1 orbital of that type is involved. Now look at how the new valence shell diagram is created for a carbon atom in which an s orbital hybridizes with 3 p orbitals. Instead of having 2 types of orbitals, s and p, there is 1 type of orbital, the sp3 hybridized orbital. Observe the distribution of the electrons. We place 1 electron in every empty orbital before placing 1 in a half-filled orbital. Since carbon has 4 valence electrons, this leads to 4 half-filled sp3 orbitals. The 4 half-filled orbitals allow the carbon atom to form bonds to 4 hydrogen atoms, which arrange themselves in a tetrahedron. Atoms with lone pairs can also undergo hybridization. Take a look at the valence shell of the oxygen atom prior to bonding in a water molecule. Notice that the 2s and 1 of the 2p orbitals are filled, and the other 2p orbitals are half-filled. When the atom hybridizes, there are now 4 sp3 orbitals, 2 filled and 2 half-filled. The 2 half-filled orbitals bond to hydrogen atoms. The 2 filled orbitals become lone pairs. There are 4 pairs of electrons around the oxygen atom, satisfying the Octet Rule. 2 pairs come from the lone pairs, and 2 pairs come from the bonds with hydrogen. This gives us bond angles near 109.5 degrees and the familiar bent shape of water. not all p orbitals in an atom have to hybridize. For example, look at the formaldehyde molecule. Formaldehyde consists of a central carbon atom bonded to 2 hydrogen atoms and double bonded to an oxygen atom. In the ground state, carbon has 1 pair of valence electrons in the 2s orbital and 1 unpaired electron in 2 of the 3 2p orbitals. When the atom hybridizes, one of the electrons in the 2s orbital is promoted to the empty 2p orbital to give 4 half-filled orbitals. The 1 electron still in the s orbital and 2 of the p orbitals hybridize to form 3 sp2 orbitals. The remaining p orbital retains its characteristics. Because the s orbital hybridizes with 2 p orbitals, this is termed Sp2 hybridization. 2 of the sp orbitals bond with hydrogen atoms, and the third sp orbital forms a single bond with oxygen. The sp2 orbitals orient themselves at 120 degrees from each other in a trigonal planar structure. The p orbital is perpendicular to the plane of the triangle. Later, the formation of a double bond involving the p orbital will be described. Hybridization of just one s and one p orbital can also occur. Following the naming pattern, this is called sp hybridization. This form of hybridization leads to 2 hybrid orbitals 180 degrees apart from each other, resulting in a linear molecule. Hydrogen cyanide is a molecule in which the carbon atom undergoes sp hybridization. The carbon atom forms a triple bond to a nitrogen atom and a single bond with a hydrogen atom. When hybridization occurs in the carbon atom, an electron from the 2s orbital is promoted into an empty p orbital. Then the half-filled s orbital and 1 half-filled p orbital mix. The sp orbitals created by this orient themselves across the nucleus from each other, 180 degrees apart. The other 2 half-filled p orbitals retain their characteristics. This leads to a linear structure. One hybrid orbital bonds to hydrogen, and the other one forms a single bond to nitrogen. The 2 p orbitals are oriented perpendicularly to each other and are perpendicular to the sp orbitals. As was the case in sp2 hybridization, the p orbitals form the multiple bonds, as will be shown later. The bond that is formed between the electron in a hybrid orbital and another atom is called a sigma bond, symbolized by the lowercase Greek letter sigma. Sigma bonds are formed when lobes of orbitals point towards each other and overlap, and the shared electron pair is centered along the axis between the atoms. Both s orbitals and hybrid orbitals always form sigma bonds. When p orbitals bond end-on with other orbitals, a sigma bond is formed. It is the sigma bond that forms first when multiple bonds are formed. Sigma bonds allow for rotation around the bond. To see what this means, look at the ethane molecule. Ethane consists of 2 sp3 hybridized carbon atoms, each bound to 3 hydrogen atoms and 1 carbon atom. In this molecule, the carbon atoms are free to rotate around the bond between them. This means that the hydrogen atoms on one carbon can change position relative to the hydrogen atoms on the other carbon. Being able to rotate allows a great deal of movement and of shape changing within long-chain molecules that have many sp3 bonds, such as the hexane molecule. Remember that in some sp2 and sp hybridized atoms, there are sets of unhybridized p orbitals. These orbitals have lobes on opposite sides of the nucleus from each other. When an atom is sp2 hybridized, there is one p orbital oriented perpendicular to the plane of the sp2 orbitals. When an atom like this bonds to another sp2 hybridized atom, the p orbitals are lined up side by side. A bond is formed by the sharing of electrons in the two lobes of the p orbitals. This forms a different kind of bond than the sigma bond, which is called a pi bond. A pi bond consists of two bun-shaped lobes, one on either side of the sigma bond. Ethylene illustrates sp2 hybridization and the formation of one sigma bond and one pi bond. Atoms that have sp hybridized have two p orbitals that are perpendicular to each other and mutually perpendicular to the sp orbitals. When an sp hybridized atom forms a sigma bond with another sp hybridized atom, these p orbitals overlap in the same fashion as the p orbital did in the sp2 hybridized atoms, again forming pi bonds. In this case, two pi bonds are created, one for each pair of p orbitals. The two pi bonds created are on planes that are perpendicular to each other along the line of the sigma bond. One example of a molecule that has sp hybridized atoms and two pairs of pi bonds is acetylene. In acetylene, two carbon atoms are triple bonded to each other, and each is bonded to a hydrogen atom. If there is one sigma bond and one pi bond between two atoms, the atoms have a double bond. If there is one sigma bond and two pi bonds, then the atoms have a triple bond. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. The length of the bond formed, which is the distance between the two nuclei, is related to the bond type. The nuclei in the atoms are brought near each other by the negative charge of the shared electrons, so having more bonds, and therefore more shared electrons, will bring the nuclei closer together. Therefore, triple bonds are the shortest bonds, double bonds are somewhat longer, and single bonds are longer still. Another characteristic of pi bonds is that they are non-rotational. The arrangement of the p orbitals in a pi bond means that for the carbon atoms of ethylene to rotate around the sigma bonds, the pi bonds would have to be broken and formed again. Breaking pi bonds to allow rotation requires energy, and because of this, it will not happen easily. In many organic molecules, the difference between whether two groups of molecules are on the same side of the double bond or on opposite sides of it is significant. This can influence both reactivity and physical properties. An important characteristic of molecules that is affected by their shape is polarity. To say that something is polar indicates that its two ends have opposite characteristics. Two common examples of this would be the north and south poles on Earth and the poles on a bar magnet. In the case of a polar molecule, the ends have opposite electrical charges. Polarity occurs because the atoms on one end of a molecule pull the electrons more strongly than the atoms on the other end. This gives each end of the molecule a partial electric charge, because the end that pulls the electrons more will take on a partial negative charge, and the other end will take on a partial positive charge. This partial charge at each end is denoted by a lowercase Greek delta symbol with the appropriate positive or negative sign. An arrow indicates the direction of the charge. The head of the arrow points to the negative end of the molecule, and the other end of the arrow is crossed, forming a plus sign at the positive end. The polarity of a substance helps to determine its physical properties, such as boiling point and melting point. The property that causes polarity in a molecule is called electronegativity. Electronegativity means that one atom in a bond exerts more pull on the shared electrons than does the other atom. This causes that end of the bond to be more negative, due to the additional electrons pulled to that end. The relative electronegativities of atoms can be obtained from an electronegativity chart. The higher the value, the more electronegative an atom is. To illustrate how polarity occurs in a diatomic molecule, consider hydrogen fluoride. Fluorine is more electronegative than hydrogen. Since the fluorine portion of the molecule is more electronegative, it is assigned the delta negative charge. The hydrogen gets the delta positive charge, and the arrow points to fluorine. Thus, a polar bond can lead to a polar molecule. Polar molecules are also called dipoles because the two poles have opposite charges. Similarly, polarity can occur in molecules that have more than two atoms. For example, ammonia consists of 3 atoms of hydrogen bonded to a central atom of nitrogen, forming a pyramidal shape. Nitrogen is electronegative relative to hydrogen, so the nitrogen end of the molecule is assigned a delta negative charge, and each of the hydrogen atoms receives a delta positive charge. Then assign an arrow for each of the 3 bonds, pointing along the axis of the bond. Since the arrows that indicate the direction of polarity don't cancel each other when added together, the ammonia molecule is polar. The firing of the capsule's rockets in this and the following scenes illustrates the way polarities interact in the molecules depicted. Some molecules contain polar bonds, but the molecules themselves are not polar. An example of this is the carbon dioxide molecule. Oxygen is more electronegative than carbon, so there are 2 polar bonds in the molecule, yet carbon dioxide is not polar. The reason for this is explained by looking at the structure of carbon dioxide. Notice that the 2 oxygen atoms are directly across from each other. This means that when you draw the arrows indicating polarity, they will cancel each other, and the net result will be a nonpolar molecule. Structures determined by Vesper Theory can be used to make predictions about polarity in other molecules as well. Water molecules are bent, with an angle of about 104.5 degrees. Oxygen is more electronegative than hydrogen, so the arrows pointing from the hydrogen atom towards the oxygen atom indicate polar bonds. Notice in this case that the arrows are not pointing directly at each other, and they therefore do not cancel each other. This means that the water molecule should be polar, because it has a net polarity. This is in fact observed in experiments. In the video, a slight electrical charge is imparted to a balloon by rubbing it vigorously across a person's hair. The slight charge on the balloon attracts the oppositely charged end of the water molecules, with the result that the stream of water is deflected. Now look at one more example. The Vesper structure for methane is a tetrahedron with a hydrogen atom at each corner. Carbon is more electronegative than hydrogen, so the arrows point from the hydrogen atoms toward the carbon atom. These polar bonds interact in such a way as to cancel each other. Because they cancel each other, methane is a nonpolar molecule. In fact, in any symmetrical molecule, the polar bonds will cancel out and lead to a nonpolar molecule. It was noted earlier that polarity has an effect on a compound's physical characteristics. 2 important physical characteristics are melting point and boiling point. At a low enough temperature, substances will exist as solids. Attraction among the molecules in a solid is strong enough to hold the molecules in place and to give a solid a definite volume and shape. As energy in the form of heat is added to a solid, the force of attraction between molecules is overcome, and the solid melts, becoming a liquid. In a liquid, the attractive forces are strong enough to keep molecules near each other and maintain a consistent volume, but not strong enough to give a rigid shape. If more heat energy is added, even these forces are overcome, and the molecules can separate to form a gas, which has no set shape or volume. Solid, liquid, and gas are called the three states of matter. Water is a good example of all three states. As you can see in the pictures, ice cubes maintain their shapes. Liquid water fills the container it's in, and the gaseous form of water, which is called steam, expands and has no set shape. The interactions within a molecule, for example covalent bonding, are called intramolecular forces. The interactions between different molecules, such as water molecules, are termed intermolecular forces and can explain the states of matter. Intermolecular forces can also explain why different substances have different melting and boiling points. There are three principal intermolecular forces, collectively known as van der Waals forces. They are named for the Dutch chemist Johannes van der Waals. One form of intermolecular force is called London dispersion. Another form of intermolecular force is called dipole interactions. This force is closely related to a third intermolecular force called hydrogen bonding. Each of these forces will be discussed separately. As we have seen, any molecule can be put into the liquid state at a low enough temperature. To exist in the liquid state, there has to be interaction and attraction between molecules. What accounts for the force of intermolecular attraction? The German physicist Fritz London explained the nature of one type of interaction that exists in all types of molecules, termed London dispersion in his honor. London noted that at a given moment in time, a majority of a molecule's electrons can be on one side of the molecule. This creates a partial charge on the molecule for a very brief period of time. This brief partial charge is called an instantaneous dipole. The partial positive charge at one end of an instantaneous dipole can attract the electrons of another molecule to move in that direction. This will cause the second molecule to have a charge and configuration similar to the first. The dipole created by an instantaneous dipole in another molecule is called an induced dipole. The attraction caused by the interaction between instantaneous dipoles and induced dipoles is weak and short-lived. The cumulative effect of these interactions, however, is enough that all substances can exist as liquids. The strength of intermolecular attraction due to London forces is lower for smaller molecules than for larger molecules. This trend can be seen in the chart of the boiling points of the noble gases shown. While the noble gases exist as single atoms, due to their filled valence shells, they exhibit properties similar to those of molecules. Noble gases increase in size going down the periodic table. In the larger noble gas atoms, the outermost electrons are farther from the nucleus, and because of this, are held less strongly than in the smaller noble gases. This allows the electron cloud of larger atoms to form instantaneous dipole-induced dipole pairs more easily, which means that the attractive forces are increased. This leads to an increase in boiling point for larger atoms. The same trend can be seen in the diatomic molecules formed by group 7A elements, such as fluorine and chlorine. Dipole interactions, also referred to as dipole-dipole forces, are related to the polar nature of molecules with permanent dipoles. The partial positive charge on one molecule is attracted to the partial negative charge on another molecule. At the same time, similar charges repel each other. Because of this, molecules arrange themselves in such a way as to maximize the attraction and to minimize the repulsion. The strength of dipole interactions is only about 1% of the strength of a typical covalent bond. Even though the dipole interaction force is weak compared to the strength of a covalent bond, it is powerful enough to keep the molecules of a polar substance together in the liquid state at a temperature that would cause nonpolar molecules of similar size to become gases. As an illustration of this, hydrogen chloride and diatomic fluorine both have 18 electrons and similar molecular weights. Because of this, it would be natural to assume that they would have similar boiling points, since attraction due to London dispersion is similar for molecules of similar size. However, the boiling point of the liquid formed by the polar molecule hydrogen chloride is almost 100 degrees Celsius higher than the boiling point of the nonpolar fluorine molecule. This higher boiling point reflects the heat energy required to overcome the stabilizing effect of dipole interactions. The third type of intermolecular force, hydrogen bonding, is typically viewed as a special type of dipole interaction. It occurs in molecules in which hydrogen atoms are attached to nitrogen, oxygen, or fluorine atoms. The atoms of nitrogen, oxygen, and fluorine are relatively small and highly electronegative. Hydrogen has no inner electron shells to screen its positively charged nucleus. And because the bonding electrons are strongly drawn away from it, the hydrogen end of the molecule becomes very positive relative to a typical dipole. This leads to more of a concentration of the charge at the positive and negative ends, or poles, of the molecule than is present in molecules consisting of larger atoms. The small size of the hydrogen end allows a close approach to the negative end of other molecules. This physical proximity, combined with the relatively large difference in charge between poles, leads to an attraction that is about 5 times as large as a typical dipole interaction, or about 5% of the strength of a covalent bond. To see an example of this effect, look at the boiling points of methane and ammonia. Both methane and ammonia have 10 electrons, and both have similar molecular weights. Given these facts, the compounds might be expected to have similar boiling points, but this is not the case. The boiling point for ammonia is about 130 degrees higher than that of methane, which does not undergo hydrogen bonding. The much higher boiling point of the polar molecule ammonia is due to the stabilizing force of hydrogen bonding. In liquid ammonia, hydrogen bonds are created between the molecules. This is not the case with methane molecules. Although hydrogen bonding is only about 5% as strong as covalent bonding, energy in the form of heat has to be put into breaking these bonds. This energy accounts for the much higher boiling point of ammonia. In this program, you have seen that small molecules commonly form 5 shapes. There are many large, complex molecular shapes that exist, especially in living organisms. These complex molecules are generally made up of combinations of the 5 common shapes, much as complex shapes can be assembled from bricks. Among the shapes that large molecules can take are rings, multiple rings, long chains, and combinations of chains and rings. Recently, scientists have even discovered ball-shaped molecules made of carbon atoms that form 5 and 6 carbon rings that come together like the panels of a soccer ball. All of these complex structures can be viewed as combinations of linear, trigonal planar, tetrahedral, pyramidal, and bent subunits. Much as the 26 letters of the alphabet can be combined to form a huge variety of words, the 5 basic molecular shapes can be combined to create a huge variety of molecules. In this program, you have learned various aspects of molecular structure. You have seen that the repulsive force exerted between electron pairs, as explained in Vesper Theory, predicts the shape of a variety of small molecules. The shape of a molecule, in turn, affects the degree of polarity of the molecule in a predictable fashion. The polarity of a molecule helps to determine its physical characteristics, such as boiling and melting points. Understanding the intramolecular and intermolecular forces influenced by molecular bonding leads to a greater understanding of why substances behave the way they do, which is the basic goal of chemistry.